I don't know how people fit them in. Oops. Yeah, I've since long ditched the 3 exams. All right, so we'll do some announcements before we get started on our last chapter. So we were kind of covering this in class. Oh, sorry, Miss Wakeham. It always is mapped incorrectly. But we are at the end, if you can believe it. I feel like the quarters go faster and faster. So our last week, we'll be doing acids and bases. As you can see, we kind of alluded to that. And then, like we're kind of going over in class, the final exams and everything is already online. Just on Blackboard, like I said, I kind of gave up on the MyOpenMath for now. But that being said, I want to give y'all like a huge thank you for all the feedback and everything. Like, obviously, I think I'm going to spend my time between the quarters preparing, since I teach this class like all the time. So that'll help me just hopefully program it for the next cohort. And so y'all will all get your bonuses and for that work. Yeah. So you get a 10% credit just for even like doing it. And then it puts you on a different scale. So then you have like a 10% bonus. I mean, I guess you would think of it as kind of extra credit since it gives you a little boost. But so yeah, anybody that did any part of it, and especially if you gave feedback, like that was really useful. And so the final and lab final are already on Blackboard. They should be under an exam folder. There's kind of like a midterm, yeah. No, like I said, I'm pretty loose with the deadlines, so it's open now. So some people were like ready to get a jump on it, and I mean, there's absolutely no pressure. That obviously helps me get, the grading done. But officially, right, if you want to take the in-person exam, it's going to be next Wednesday at our usual class time, and we'll review on Monday like we usually do. But you could take both as again, yeah. Yeah, the format's going to be about the same. So the in-person one's going to be 2 hours. I forget what the online portion is. Yeah, they're just like, they're slightly different, right? Because the in-person one is more, I would say, free response. The online one's more multiple choice. But we also notice that there's a grade discrepancy. So I will take that into account, right? So if you take the in-person exams, I know that the in-person exams just like score lower. So there's going to be some grade adjustment. So like, whatever modality you take it in, don't stress about your grade. The biggest thing I'll say is turn everything in. And I think most people have been keeping pace. I neglected your class, admittedly. So I caught up on everybody else. Then I neglected the in-person people and your Blackboard. But I will do that between now and Wednesday so you guys have a good picture of where y'all stand. All right, is that, oh. No, it's just a lab final. And so if you want to just take it on Blackboard, for the in-person folks, just take the second one. There's a first one, but you don't need to worry about it. Yeah, so that will cover our stuff, but there will also be an in-person version if you want to take that with like a minor thing to do in lab, but it should be easy, either version, but pick your poison. Any other questions, comments? All right, well, hopefully you've had a fun time. The quarter sped by as spring quarter does, but all right, so our last chapter, and we were kind of touching on this with the solutions. And so now let's just take a look at, well, what is an acid in terms of what are its properties? And it has a sour taste. You probably know this from anything from fruits, right? I'll put like citrus fruits. There's a lot of different, so obviously there's citric acid, but I want to say malic acid, if I didn't mispronounce it, is also in fruits and a variety of other natural acids. And then I don't know if y'all are addicted to the sour candy like I am. You like sour candy? Yeah, yeah. So check the back of the ingredients next time, right? See what acids. There's some sort of organic acid. Usually it's citric acid is the main one, but like I said, check the back of your favorite candy and kind of see what organic acids are used to make them sour. And then like we've seen, right, we saw how HCl dissolved our magnesium, for instance. They can neutralize bases, so we did that with our acid-base reaction. It can also change, right, blue litmus paper to red. I think you guys had the privilege of using the universal indicator. And so we'll go back to, again, what's a strong acid, what's a weak acid. So there's hydrochloric, so I'll put this as a strong, since it fully disassociates. And then remember we have our organic acids with this carboxylic acid group. So anytime you see that, and some of your organic acids may have several groups. So looking at acids, so you have like hydrochloric acid in your stomach, for instance. So of course that helps break down your food digestively. Acids are also used in metal cleaning or food preparation, a lot in like ore refining as well, and trying to get out metals. Sulfuric acid, you might know that it's used in batteries, also used in like fertilizer and explosives and electroplating copper. Nitric acid, some more right explosives and fertilizer manufacturing. So acetic acid, you know, is vinegar, and obviously, right, that's used in food preservation. Citric acid, so like we'd mentioned, you see it in a lot of candy, in addition to other organic acids, and obviously it's in your citrus fruits naturally. And then carbonic acid is in our fizzy water, for instance, and that's just, we'll look at the equilibrium, but it's essentially, right, dissolving our CO2 in water gives us some instance of carbonic acid. And then hydrofluoric acid is used for glass frosting and etching, and that's always the one that's like in the movies, right, is eating through the tub and stuff. And I mean, you do have to keep it in a plastic container, so that is a safety issue with HF. It also goes into, well, HF is also toxic, so I don't know. So HF, right, as you can see, is used for glass frosting, so that means you can't store it in a glass bottle. And then, sorry, I was trying to find the exact component for hydrofluoric acid. And so the other issue with hydrofluoric acid and why it's pretty dangerous is if you get a drop on you, it has the potential of going through your glove, and then you might not notice it, so it might not burn like the other acids. But what it does do is it can dissolve like the calcium in your bones. And so if you're working with HF, you have to have this compound. It's a safety thing called calcium gluconate. So if you were to ever get it on you, you put that on, wherever you made contact with the HF, and then it should react with the calcium, obviously, in that compound, as opposed to uh, anywhere in your body. And of course, the problem with that is, right, it can like re-solidify to that calcium, and depending where it re-solidifies, right, it could cause strokes. It's not good. So yeah, be careful with HF. And then phosphoric acid is famous for being in beverage preservation, like sodas. No, I forgot what the sodas were called. You guys, they're called like phosphorus drinks or something. Remember, like way back in the day, like when the soda shops open. I think that's what they're called, the phosphorus drinks. Well, there's a soda shop in Grants Pass, and it's like in the Grants Pass pharmacy, and they do this like I want to say it's called phosphorus soda, but it's supposed to be more medicinal. I don't know. But anyways, that's kind of where this whole phosphoric acid thing and soda started, and it started as some sort of like health drink too. But anyways, you should check out that soda shop in Grants Pass. All right, so like we kind of touched on, so the organic acids are going to be our weak acids, meaning that they do not fully dissociate. And so they're easily identifiable by that carboxylic acid group like we mentioned. And so I think we already named these. Again, check your bag of candy next time. But we have either citric acid or malic acid is another common one used. Or tell me what other ones were used. I mean, that's kind of the beauty of like food chemistry. And also like the beauty of chemistry, right? Like you can get into really any industry you're interested in. And so food science is a huge one, right? Every company needs a chemist on staff. I know the job market's bad. There's always a joke for chemistry. It's like, yeah, the job market's bad for chemistry, but it's always bad for chemistry. And that's always because like a company just needs like one chemist, but if you can fill that role, if you can be, the food chemist and kind of help develop things. And now with all the different gelatins, like that's how they make the best gummies now. Anyways, but that's some fun R&D if you can develop different products. All right, looking at bases for a second. So bases you would not want to eat. So they taste better. And I don't know if any of y'all grow potatoes, or maybe you've left your potatoes exposed to the sun, right? And they turn green. And so that green compound that your potato is producing is an alkaloid. And so if you were to try to consume the potato, which I would not recommend, right, it would taste bitter. And so you would know that, oh yeah, my potato did go bad. And again, that's kind of, right, nature's way of telling you, hey, poison, poison. And so that's why it probably tastes offensive to you and any other base products. I would say maybe you had your mouth rinsed out with soap, but I think that's like a child abuse nowadays. I don't know. And then bases also feel slippery to the touch, so you probably know that with soap. I don't know if you've gone around touching bleach. I mean, you probably shouldn't do that. But you would know bleach feels slippery. And then, of course, they can neutralize acids, change red litmus paper to blue, or again, we had our universal indicator. Oh, tonic water is another base that you don't often think of. And, well, something to try. So tonic water has quinine in it. I probably misspelled that. But I haven't tried this. I want to try it this year. So this is an organic compound. And so if you apparently maybe like concentrate it a little bit and make like jello shots or something out of it, you can get it to glow in black light. I don't know. At least that's what the internet says. I don't know, like, if there's enough quinine. That's why I think it suggests, like, kind of concentrating it. So I'll have to try that experiment this summer and report back. But just want to let y'all know in case you wanted to play around. Since, I mean, Halloween will be here before we know it. Unless you want to make, like, radioactive 250 jello shots, you know, non-alcoholic. All right, and then, so other uses for bases. I think we kind of touched on this with the polar non-polar thing, but we mentioned that these different bases have been used in like soap manufacturing. So anything from sodium or potassium hydroxide, or kind of our sodium carbonate, like our soda ash. So those are also all bases. And then you can also buy these things online. If you ever wanted to get into soap making, we do have like local handmade soap companies, but I was kind of saying that's why you see so many at the farmers market. You can do it too. And then other uses are, of course, just like petroleum processing, plastic manufacturing, cotton processing, more battery production. Obviously, we have sodium bicarbonate, that's baking soda, and that's used in so many things, right? People use it to pH balance and cooking and acid. Maybe use it as like a natural shampoo. So all different household uses. Sodium carbonate, so that's a water softener in addition to the soap manufacturing. And then we have ammonia, which is again more fertilizer and explosives manufacturing. Alright, so this is some kind of formality now. So basically it's saying that water doesn't just disassociate. And so basically it's saying, right, that this little proton can't just exist by itself. And so if we were to draw out the true mechanism of what happens, so the reaction is we have two water molecules, and they're kind of staring at each other, and then a small portion of them could react in such a manner where this oxygen deprotonates the other one, and then we formally make this hydronium. Let me draw it out. And then if we did some arrow pushing, so this grabs this hydrogen, those electrons go to the OH, that gives us, right, our negative OH. So electrons are balanced there. And I mean, this is all to say, I like to say chemists are kind of lazy. And so you often see chemists like still put H plus, right? So we'll still use H plus, but just know that we really mean hydronium. So anytime you see H plus, it equals hydronium. So they're pretty interchangeable. But again, we're not saying that they can exist. They're just too small and too, right, like naked and reactive, so they'll just pair with the water anyways. And I mean, I don't quite like how it's shown here, because that, to me, that implies something different. So I'll go back right to this model here, where again, action starts at the electron. So your electrons are going and plucking off that hydrogen. And just beware for bad mechanisms on the internet on that as a side note. So if you ever see like H plus attacking, that's technically an incorrect mechanism. At least any true chemist would say this, but like I said, you can find anything on the internet, so just watch out for anything that has bad mechanisms. You always have the action from the electron, so that's where any good mechanism will come from. All right, let's look at our definitions. And so this is kind of our overview, and then we'll go deeper. And so we'll start with our Arrhenius definition, and we'll see it's kind of like the easiest to understand. It's the ones that we've worked with, but then we'll go into the exceptions here. And so looking at Arrhenius theory, we say, well, anything's an acid that produces H plus ions in aqueous solution. And so you have your HCl, and then, right, it disassociates, and here you have your H plus. Again, right, we know it's not H plus. Technically, a water molecule is coming along and, right, kind of instantaneously plucking this off to make that disassociation. But like I said, we're usually just shorthand it. And then our other definition, again, our simplest definition is our bases produce hydroxide ions. And so these are like typically the compounds that we think of, obviously sodium hydroxide, potassium hydroxide, calcium hydroxide, magnesium hydroxide, okay, lithium hydroxide. Sorry, now we're going overboard. But okay, you get the point, right? Any of our ionic compounds with hydroxide attached there, again, for the most part, they fully disassociate. So going back to our solubility rules. And so there's our hydroxide. Okay, so there's our base definition. And again, HCl, strong acid, fully disassociated as depicted here. Sodium hydroxide, strong base, right? It's from our salt. So fully disassociated in solution. And again, I'm saving the demo for Wednesday, so we'll see. I'll bring the full spread. And so like we said, we can do our acid-base reactions, so our simple Arrhenius acid-base reactions, where they just kind of recombine as our double displacement reaction. So looking at this example, so just rewrite it and dissect it. So we have our strong acid, right, plus our strong base. And then they're going to swap cations or swap partners here. And so we can also think about it as a double displacement. Right, so our neutralization is a type of double displacement reaction. Again, being driven forward by the formation of water, right? Kind of think back to our solubility rules. Everything's just coming together. And so, yep, there's our neutralization reaction to make HOH. And so you might see this as another way to represent water as HOH. You might want to write it as HOH for this chapter as well, just so you can see the stoichiometry, right? So right now we're in a 1-to-1 ratio. And so, right, we're going to be practicing a little bit of stoichiometry again. All right, plus, and then we said, okay, for these neutralization reactions, we said that they produce water plus the salt. And so our other partner form is our sodium chloride. Yeah, question? Oh, well, that's what we're going over, right? So this is kind of the first definition and how it started, right? So they're like, okay, we'll look at these basic acids, and so anything, again, that produces this H plus ions in solution is an acid. And so we'll kind of get to this, so maybe you'll understand it a little better. But basically, there's some sort of ratio of ions of hydronium and hydroxide, and that gives you your pH. And so that's how it kind of started. It's like, okay, well, let's measure these H plus ions. Where do they come from? Kind of what does their molarity correspond to? And like their pH. So yeah, we're slowly getting there. But let's keep going. So to your point, this was, again, kind of just like an early working definition, and it worked for most acids and bases, right? So again, you've played with these in lab, so these are kind of common acids and bases, but it doesn't explain everything. And so it doesn't explain why ammonia is a base, right? Even though there's no hydroxide ions, at least when we write it like so. And we'll finally maybe really explain why the stockroom writes ammonia as ammonium hydroxide. And because, right, they're the same in equilibrium. And we'll look at that. And then it also doesn't explain how sodium carbonate or sodium oxide are also basic solutions, even though they don't have hydroxide ions. So, right, so not the full picture is given. And then it doesn't explain why CO2 can form acidic solutions, even though it has no H plus ions. Okay. And then it also doesn't explain any acid-base reactions that occur outside, right, our aqueous solution. So then this was kind of the next attempt to develop a working definition. And again, this is, right, all building on your question, and that is the question is like, well, how do you define it? And then I won't get into it in this class, but like there's this thing called a Hammett plot, and that is what a real research chemist would do. I've never actually done one, but if you cared about like how acidic, that would be what you would do. But anyways, so back to our definitions. And so now they tried saying that let's define things as either proton donors or proton acceptors. So either donating or accepting. But again, we're going to see the shortfalls of this definition. So good enough for our class, but doesn't get into everything. And then the other thing to note is each definition is all-encompassing. So, right, any acid-base reaction that fit our Arrhenius definition will also fit this Bronsted-Lowry definition. Okay, so then they attempted to define an acid as then, so still an H plus ion donor. And then our base is our H plus ion acceptor now. And so now, generally a base is something with some electrons, right, to, like we said, attack or deprotonate that ion there. And then, again, our acid molecule donates our H plus ion to our base. And so this is a good one to start thinking about what we did in lab again. So we did our titration. And so let's rewrite our acid. So we worked with vinegar or acetic acid. And then we reacted it with our base. I'm trying to color code, but I'm not doing a very good job. So then base, sodium hydroxide, and again base. Comes along, deprotonates there. And then this is our conjugate base. So now our deprotonated acid, so this species. And then, right, it's picked up our counter ion, our salt. So now this is sodium acetate, for instance. Or whatever your corresponding salt is, but generally, right, well, if we added sodium hydroxide, it's going to be sodium acetate. And we do, we'll get to buffers, and so we also like have this in lab. And then our conjugate acid, so again, this is our conjugate base. And then now our hydroxide, right, picked up a proton to form water. So not forgetting where that other proton came from. And so now we have water. And so now formally this is going to be our conjugate acid there. And so just take that in for a second, right? So notice how our acid species had a proton, base comes and deprotonates it. And so now let's look at another example. Oh, sorry, base deprotonates it. I got too excited. And then again, right, our acid deprotonated, conjugate base, like sodium acetate, and then our conjugate acid, in this case, water. And so let's look at now our ammonia in a little bit more detail. And so now this explains ammonia. And so let's draw this out. So this is where our Lewis dot structures come into play and help us again see reactivity. And so here's our lone pair. We have our water. And so that means that this ammonia can come and deprotonate this. And then this makes ammonium. And then again electrons, so these go back here to make ammonium hydroxide then. And so that's why, right, in solution, so ammonia dissolved in water is ammonium hydroxide. So that's why the stockroom again calls it such. So they label it, right, ammonium hydroxide, but as implied by this equilibrium arrow, right, some of it will be in this species, so as ammonia, and some of it will be kind of disassociated and then forming some amount of base there. Questions so far on this? All right, so just kind of reiterating that. And then something you'll have to do in your homework is kind of identify these conjugate acid-base pairs. And so in our Bronsted-Lowry acid-base reaction, our original base, like we saw, becomes our conjugate acid. So again, like for example, hydroxide became water, and then our acid, like our acetic acid, became the conjugate base, right, acetate. And so now let's note something. So right, this reactant and product is called our conjugate pair. And so we can always identify a conjugate pair by the difference in our proton. And so they're always one proton difference, right? So going back, okay, well, hydroxide and water, right, one proton difference. Acetic acid and acetate, one proton difference. Looking at here, right, so if we're adding an acid, that's going to go from a base to an acid then. And again, one proton difference between our ammonia and our ammonium, so our base and acid. Notice the acid is always going to have more hydrogens as well. So maybe say that. And then, again, our other pair, so water and hydroxide. So we can identify our acid-base pairs. And so before we do this example, so you don't want to get fooled by anything. So what's the problem with this? Or is this a pair? Is this appropriate? Exactly. And so that's what you want to watch out for. So this is a trick. So it's a 2 proton difference. So exactly, it would not be correct. So you only want a 1 proton. And so always look for that. You're like, okay, how do I just either add or remove 1 proton here? All right, so let's take a few minutes to look at this example. And so it asks us to identify our acid and base initially, and then our conjugate acid and conjugate base. Like I said, let everyone look at it for a minute or two. So let's start with A. So what do we get for our H2SO4, which is sulfuric acid? So acid or base. Yeah, so it's an acid, and I mean, it's kind of given away in the name, and water. I don't think we've stated it formally, but it is amphoteric, so water can act as an acid and a base. But we are also noticing the role and what happens, right? So it started off with 2, then it goes to 1. So good. So this is supplying our protons. So that's our acid. That makes water our base. And so now looking which species is our conjugate acid. Or, yeah, the hydronium. Yeah, so conjugate acid. Good. And then this leaves this hydrogen sulfate. Excellent. Conjugate base there. All right, let's repeat that for B. I'm going to swap my colors. So now really looking at now at part of the equilibrium process that goes on. And so one of the steps is we have our hydrogen carbonate can react with water to form our carbonic acid again and hydroxide. And so what is water acting as this time? Acid. Excellent. So right, it gave up its proton. So our hydrogen carbonate is our base then. And so what's our conjugate acid? So carbonic acid, good. So conjugate acid. And then this is conjugate base. Good. And then just so you can kind of, again, get a sense of the water equilibrium process. So, right, you have CO2 getting dissolved. So you have this carbonic acid. So really there's a lot of layers to it. Sorry, let me put this. So let's do on a side on ocean chemistry. And so, okay, we had this process, right? But then we can have, so our carbonate. And so the ocean has a lot of carbonate in there from seashells, obviously limestone. And so this carbonate can react with water. And so that gives us the first one, our hydrogen carbonate, right? Which then goes on to the next process. And then it also depends on how much CO2 is dissolved. So, right, CO2 and water form our carbonic acid. And so we have this whole big equilibrium thing to think about and kind of what's happening. So not to get too much into it, but I wouldn't worry too much about like CO2 and everything, because everything is in one huge equilibrium that will eventually equalize out. So, right, depending on the temperature, so we kind of learned it last week with solubility. As temperatures rise, sometimes they can cause a bit of CO2, right, to be released, or vice versa, right? So if it's cold, it'll dissolve. And then, but of course, if you have more acid being formed, well, then it's going on and reacting and being neutralized by our calcium carbonate. And so it's just all one big equilibrium reaction there. Anyways, so we won't get into all the details, obviously. But, I mean, you can see where it'd be a good research vein and to kind of see localized minimas or maximas, especially due to like pollution. So that's where you can have like, I would say, environmental issues stand and actually need attention. Anyways, so like we were looking at, now we're kind of looking at it from our acid-base lens. Oh, before we move on, we neglected our Lewis definition. So as you can tell, we're not really going to touch on this in this class, but I do want to give a typical Lewis acid-base pair. And so I want to bring it up because it is a hot area of research. And so sometimes these are also called, or at least when they do them in research, what they're trying to do is frustrated Lewis pairs, it's called. And so, well, let's go over what is a Lewis pair. And so you have, let's say you have boron trifluoride. And so we've touched on the fact that boron is interesting, right? It only has 3 valence electrons. It only makes 3 bonds. And so it's electron deficient, right? It still wants those 8 electrons. And so when someone like nitrogen comes along, again, you already remember nitrogen has those 2 lone pairs. And so it would want to come and donate to this boron. And then the vein of research and this whole frustrated comes into play because they might try to make some sort of ligand motif to hold the boron and nitrogen at a distance so that they can't react directly, but maybe they have to do something, and the idea it does something cool. But that's where that goes. But again, we're not going to go into that in this class. All right, so back to our strong acid versus our weak acid, weak base. And so again, it has nothing to do with like how dangerous it is or anything. It's just asking, do we have complete ionization of our acid or base in water? And then again, like we kind of mentioned, our weak acids only have our partial ionization. And for our purposes, these are generally our organic acids. And then we'll look at others, right, like HF. And I might print you out a cheat sheet, actually. Uh, so we'll come back to this trend. So this is the cheat sheet that I realized I probably should have printed out. So I'll probably do that during our break. So we'll take our break in a few minutes here. And so let's kind of look at some things. And so we have our strong acids up at the top here. And so these are our strong acids. So perchloric, sulfuric, hydrogen iodide or hydroiodic acid, hydrobromic acid, hydrochloric acid, nitric acid. And again, those undergo complete ionization in water. And so let's kind of look at this base. And so looking at our acid-base chart, so our strongest acids are up top, and then we have our bases, and notice they make conjugate acid-base pairs. But these bases down here, right, are the conjugate bases of these strong acids. But let's see what this means. Well, if you have something like HCl, and again, right, it fully disassociates. We're using our single arrow. We're saying that if we put, for example, chloride in solution, it is never going to react with water to reform HCl. So just put a big X through that, right? So we're saying that basically chlorine is such a bad base, right, it cannot deprotonate that. And so that's true, right, for all these. So you could put these salts in, and they would be neutral. So this is getting to kind of the last part. Also, I'll say neutral salts. Versus, so now let's look at, well, what makes an acid or a equilibrium. Sorry, trying to find some good space. And so let's compare that to HF. And so HF, right, does have this equilibrium. And so what this equilibrium is implying is if you have a fluoride salt, and then you do put it in the presence of water, we're saying that this will act as a base. And so now it would deprotonate, it would reform HF, and it would make hydroxide ions. And so definition of a base. And so there's two things that this kind of means is, well, you have to be careful with working with fluoride salts and make sure that you quench it sufficiently and make it all basic, basically, because you don't want any of this in equilibrium. So something like sodium fluoride in solution, though, so if you dissolved this salt, so A, you have the danger, obviously, of HF. So that's kind of danger, danger. So I don't recommend working with fluoride salts. Or again, you have to be really cognizant of what happens to that waste and what pH that waste is at. But this would also mean that if you dissolved it in pure water, it would give you a basic solution from those hydroxide ions. All right, let's take a little break, and then we'll come back to these trends. So I'll probably run, and like I said, I'll try to print you this chart out so you have the reference. Homework's over there. I think that's all the handouts we need this week. All right, let's take a 10-minute break. We'll be back at 2. I'll grab handouts and let me know if you need other things. Alright, so grab the handout. Alright, so now let's go back and look at some of our other, and these are just general trends. And so now this is kind of like some saying, and this kind of goes back to what we had gone over. So let's look at our saying here. So it says, the stronger an acid is at donating a proton, the weaker the conjugate base is at accepting a proton. And so I would take this back to our strong acid versus weak acid case. So again, we're saying that this is so good at donating a proton that now our chloride, right, is never going to reform HCl, right? It's always going to be in its deprotonated form. Versus HF, right? So now it's a weak acid. So then your weak acid would then make a weak conjugate base, which can reform. And then kind of other trends that you will notice is that a higher oxidation number also gives you a stronger oxyacid. So for example, the difference between sulfuric acid and sulfurous acid. So sulfuric acid is a strong acid, excuse me, and sulfurous is a weak here. And we can tell by our equilibrium, so going back to now our handy dandy chart, and so now I'm trying to find it. Well, maybe that one's missing on our handy chart. So let's try another one. So nitrate and nitrous should be on there. And so there's nitric acid, so that was one of our strong acids, versus nitrous acid. So nitrous is a weak acid, so that again just means that displays equilibrium between the nitrite. And this could also get into like somewhat of acid rain chemistry. And so depending, if you have any sort of, this also gets into like what is dirty coal. And so something that's just dirty coal tends to have more impurities, such as maybe some of these like sulfates, sulfites. And then you can tell that these ions, right, can react with water since we have this equilibrium here to form kind of nitrous acid or sulfurous acid in the atmosphere. But again, right, the Earth, one big equilibrium cycle. So you could have, right, some acid rain, but then it gets neutralized later by some calcium carbonate, or aka limestone locally. And then our cations, and this is something else, is like if it's a cation, it's probably an acid or neutral, right? So cations tend to be either acids or they're neutral. And this will kind of take us back to the salts. And then neutral molecules are going to be stronger acids than anions. And with that being said, well, right, we said bases are things that donate electrons. So anions tend to be bases of anything. And so again, just kind of looking at what this is saying, well, we have a cation. We also have another proton here. So our hydronium would technically be stronger than our water in terms of acid strength. And acid strength could be measured in H plus concentration, or like I said, the Hammett plot. But we're definitely not going to go there. And then hydroxide, right? Obviously, it's not an acid. It's a base. So same thing, we can compare our ammonia versus our amine versus our amide. And our amide is a base. And then trends in base strength are the opposite. So like we were saying, right, our anions tend to be bases. Cations are either acids or neutral. And same thing with bases, right? They're either bases, or excuse me, anions are either bases or neutral. All right, going back to this kind of cheat sheet. And so again, just kind of appreciating now this middle chunk is where we have like our weak acids and bases. We have our acid-base pair. So again, right, I'll point out HF and fluoride, nitrous and nitrite. So we do have like potassium nitrite in lab. There's acetic acid and acetate, right? Again, acetate is the base. Sodium acetate. Again, commercially available. Carbonic acid versus hydrogen carbonate. And again, you could buy something with some sort of counter ion, so sodium or potassium hydrogen carbonate. We have hydrogen sulfide, and then again we could have sodium hydrogen sulfide as a reagent. Then ammonium and ammonia. Hydrogen cyanide is a weak acid. Then we have cyanide. So that's another one that I would say, right, kind of be cautious. I mean, I wouldn't work with like cyanides, or if I were to, right, you have to be very careful because you don't want to form hydrogen cyanide. So that's toxic. So again, that's one of those, be careful if you were to ever work with the salt of that. And so again, hydrogen cyanide is pretty toxic, and I think if you smell it, you're pretty much dead. Or and then I don't know. There are stories. So apparently, like cyanide compounds smell like almonds. So if you ever like say, "I smell almonds" in lab, people would generally start flipping out. One of my friends did that unintentionally, and so she freaked out the lab. But they did not release any cyanide compounds that day. But and then we have our carbonate, hydrogen carbonate, and then water has our base of hydroxide. And then looking at these again, these undergo complete base ionization in water. So if we were to have like metal hydrides or amides, but we usually won't see too many of these. And then just pointing out, like, these are not acidic. So ethanol does not have an acidic proton. Ammonia, right, so it gains a proton, but it's not going to lose and disassociate, right? So that's why it's here. Questions on this or anything so far? All right, we'll keep it moving. And so we won't get like too into this. This is kind of like touching on our equilibrium. Like I said, if you're in the 200 level class, we would be quantifying this, and I mean, you spend at least 2 or 3 weeks on pH and equilibrium and all this good stuff. And so all we want to say, if we can think back to equilibrium, so we have again our HCl disassociates to H plus and our anion or chloride. And so now we're saying, okay, our strong acid, and if we remember our equilibrium, it was essentially products over reactants. And remember, they're raised to the power of their coefficient and the concentrations. Well, okay, so all we need to take away, so our strong acid has an equilibrium constant that is much, much greater than 1. And so if it's much, much greater than 1, we're saying it's all product dominated. So Ka greater than 1. And so again, that's where we can state that 100% ionization occurs. And so what we're saying with our Ka being so high, we're saying our equilibrium lies all the way to the left there. And so we have, again, our 6 strong acids corresponding to up here. And well, let's look at a weak acid. So like we said, okay, well, a weak acid is only partially disassociated, but what does this mean? And so a weak acid will have a Ka less than 1. So now I'm just kind of thinking of HF, and there's some sort of equilibrium. Again, products over reactants. And now we're saying we're probably going to have more reactants. If it's less than 1. And that's where we come up with this small fraction. We could, like I said, we could quantify this. We're not going to go there, but we can exactly quantify, right, what portion of it is disassociated and then calculate all sorts of fun things. And this is, once again, reiterating our carboxylic acid group. So all of those organic ones, right, have our carboxylic acid from our carbonic, which is kind of the simplest one, and formic there. And so then our strength is measured by our Ka, and then we have our Kb, which is corresponding. And so the farther the equilibrium position lies towards the products, the stronger the acid or the base. And so looking at this, we have 1.1 times 10 to the negative 2 versus 4.9 times 10 to the negative 10. And so that's telling us that this hypochlorous acid here is stronger. And then again, our position of our equilibrium depends on the strength of our base there, which means the strength of our attraction between our base and our H plus. And our stronger attraction means a stronger base or weaker acid. So yeah, just get like big picture ideas. And so this is just kind of re-quantifying our Ka. I probably wouldn't get too wrapped up in it. Like you could look at this and hopefully relate it back and at least kind of understand it. But like I said, we don't want to get like too wrapped into it. We're appreciating it at this level. We're not going to do much to it. Yeah. Probably not too much. I mean, there's going to be like identifying acid-base pairs, but I don't think we're going to do anything with this ionization constants. Maybe the most would be like which is a stronger acid, right? This one or this one. But we're not getting into this equilibrium math. Yeah. So that's what, like I said, the 200 level chem is for. We could at least, like I said, I don't think you'll be tested on this, but we can at least appreciate this over here. So this is a nice chart. I just didn't want to print it out because, like I said, it's not too relevant for you guys in the sense that we're not going to get into all the math. But we just want to appreciate our Ka number. And maybe you want to put that like up at the top. These are our stronger acids. Again, comparatively speaking. So now I'll put stronger, right? But these are still all weak, right? So weak acids. But the strongest ones are at the top. We can tell that by the Ka. So that's, again, all we need to be at your level is like, okay, I can tell that this number is larger for my Ka value, so that's going to make it a stronger acid. Notice what it does to the pKa value. So let's look at what pKa is. And so pKa is equal to the negative log of our Ka value. And so we can plug in, sorry, I forgot to get my calculator. And so this last unit, sometimes people struggle with the calculator issue, right? So you have to have a calculator that can do base 10 logs. So if you need to borrow one, let me know. I'm okay with phone calculators. I think most of them should have log. You just might have to go into like a slightly different mode or something. Otherwise, there's like Desmos, Wolfram Alpha for online calculators. Yeah, see, I'm glad you know Wolfram Alpha. Like, one class stared at me like completely blank. No one knew it. So let's plug that in. So negative log of 1.1 times 10 to the negative 2. And then often with these numbers, you will find a lot of discrepancies. They can vary. This one matches nicely with everything, so we do get 1.96 for the pKa there. So now we see the larger the pKa value, the weaker the acid is. So it could be slightly confusing. A lot of students get confused with that, including myself back in the day. And pKa's also only really come up more aggressively in like OCHEM, and then your professor would be talking about all sorts of things of pKa. But like I said, that's kind of way beyond this class. But you could at least like appreciate where this is going and where you could take it and how far you can take it. And so now we're just kind of taking in our acid, just looking at them. So HF is, 6.8 times 10 to the negative 4 there, just so you have context. Benzoic acid is kind of common, although I'm not really sure where y'all would have run into it. There's acetic again, good old vinegar. Phenol is another acid. It is unusual, so notice phenol is remarkable because it has an OH, right? And we had just finished saying that typically alcohols are not acidic, but in this case, the negative charge is stabilized by this aromatic ring, so it is slightly acidic. And right, it is 10 to the negative 10, so it is pretty weak, right? But it still is somewhat acidic there. All right, so now here's formally going over our autoionization of water. And slowly this is bringing us to pH, but just kind of follow with us. So like we've seen, water is amphoteric, and so amphoteric just means it can act as an acid or a base. And so therefore that means that we must have a few ions present, and I'll rewrite it. Oh, amphoteric. And so I'm just going to redraw what we did earlier so you have it fresh in your mind once again. And so we see the action starts at our oxygen and can deprotonate to make our hydronium and hydroxide. Or, right, the H plus and OH as shown above is kind of our shorthand. And again, you will commonly see it abbreviated as such, and I will use the abbreviation. And so now we see that this occurs about 2 out of every 1 billion water molecules. And so this is where this number comes from. And so basically, right, they're like taking pure water and trying to figure out the concentrations of these. And so this is where they kind of landed, right? Well, they determined that our hydronium concentration is 1 times 10 to the negative 7 molarity. And this is all at 25 degrees Celsius. So there's like small variations with temperature. And then they found that the concentrations were equal. And so again, we're kind of getting at, well, this is our definition of pH 7, right? So again, they like, this almost sounds circular, but so okay, they have to start with pure water and figure out, right, what that is. So now we're kind of building to our pH scale. And so the other thing they found is that the product, so right, if we multiply them, they found that it's always the same, again at our room temperature. So small variations, but for our purposes, it's always 1 times 10 to the negative 14. And so again, we can start to piece this out. And for clarity's sake, so if we take 1 times 10 to the negative 7 times 1 times 10 to the negative 7, or just square it, right, we get 1 times 10 to the negative 14. So that's important. And I mean, maybe you can see it already, but we're almost to defining why our scale is such. All right, so this is an important relationship to help you guys too with the math. And so again, this is just defined as Kw, which is called our ion product of water, or our dissociation constant. And so note that they're inversely proportional. And so if our hydronium concentration increase, then our hydroxide decreases so that our Kw, or 1 times 10 to the negative 14, stays constant. And okay, so all aqueous solutions contain some amount of hydronium and hydroxide. And so again, right, kind of the definition then of a neutral solution and how they determine this is that it has equal amounts of hydronium and hydroxide. So both 1 times 10 to the negative 7. And then anything that has a larger hydronium concentration, then that's considered to be acidic. And then of course basic is the opposite, where we would have more hydroxide ions in solution than hydronium. All right, so let's try this, and then we'll kind of like, I feel like, do the reveal. But this is, let me scroll up, sorry. I didn't realize this was high. So see if you can do those, or take a second, a minute or two, and then we'll go over them. All right, let's see how we're doing. Oh, I forgot to mention, I would really love positive course evaluations. I really need the help. I apologize that my open math thing really didn't work out as well as I had like envisioned, and I'm sorry you guys are kind of the guinea pigs for that. But I would really appreciate any positive reviews. Keep having a lot of management issues, so I really need anything positive.
Should we do one for both the lab and this one, or should we just do one and combine the two?
I really don't know because I think they like separate them. So if,
We could
like,
have one for each class on Blackboard, and since the two
y-
classes are separated.
yeah, I mean, at the very least, I would say like, please just do one. Yeah, at worst case, copy paste maybe. But yeah, I would like super appreciate it. All right. So continuing on, so what do we get? And so for this one, like I said, I feel like now we're doing it the cruel way. But let's see how we would solve. So again, we have our H plus times hydroxide concentrations is equal to Kw, or 1 times 10 to the negative 14. And so looking at this, can we tell, is it acidic, basic, or neutral? And check one more time. So it's hydronium concentration. So you're kind of comparing it. So like 1 times 10 to the negative 7 is neutral. So then if it's higher acid or hydronium, then it's
But that means it has less hydronium than hydroxide,
all
or?
right. So then it's going to have. So let's calculate that. And so that was kind of the second half of this is calculate our hydroxide. So then we can do 1 times 10 to the negative 14 divided by our hydronium concentration. Oops. And so that means our hydroxide is 1.3 times 10 to the negative 10. And so now maybe we can tell a little bit better, right? This is tiny, this is bigger, so is this acid base?
Okay, so it'd be an acid.
Good, so acidic.
So this would be like 10 to the 14 divided by 10 to the 5.
Yep. So yeah, you can kind of like mental math it too as well. And then what about this one? So let's do kind of the same thing. You could maybe mental math it. You're looking at the number, right? And it's negative 9. Oh, sorry. I wasn't paying attention. So 1 times 10 to the negative 14 divided by 1.5 times 10 to the negative 9th. And so that gives us 6.6. 7 times, oh, I said 6, 7, times 10 to the negative 10 for hydroxide. So is that acidic or basic? Yeah, so basic. And then the last one, so then we can,
What's the cutoff again? What's considered acidic versus basic?
it's literally like neutral, has to be 1 times 10 to the negative 7, and then anything with a higher hydronium concentration is acidic, and anything lower is basic. So then if it's exactly 1 times 10 to the negative 7, so neutral, and then I think we can mental math this one. That's 1 times 10 to the negative 7 molarity for hydroxide. Good. And then, so like I was saying, I felt almost a little cruel for presenting it in this manner because I think it's a little easier to convert it to pH then. And so how we measure pH, or what it is it's our negative log of our hydronium concentration. And so now we can go back to these and plug them in, and then it'll probably be easier to determine an answer. So negative log of 7.5 times 10 to the negative fifth. So then that gives us a pH of about 4.12 there. And with pH, you always gain an extra sig fig, but now I forget the exact kind of mathematical reasoning why something of logs and sig figs, but like I said, I don't have quite the good mathematical explanation prepared. All right, let's try that again for our basic one. So negative log of 1.5 times 10 to the negative 9. So 8.82, and so now that's right greater than 7, so that's basic.
So it would just be the negative log of whatever we got.
Yeah, for the hydronium. And so negative 8.82 for pH. And then let's just, I mean, maybe you can do this one in your head, right? I can't do these decimal ones, but so the log of 1 times 10 to the 7, I guess let's plug it in, but mental math, right? 7. Always good to practice your mental math. Yay, 7. So confirming neutral. And so, right, it is a logarithmic scale. So we're seeing that anything, right, that deviates by one number in pH really deviates by times 10 in concentration. And then just kind of giving us some context. Oh, yeah.
So like if you were using a 0.1 molar acid, it would be effectively 1 pH lower than the 1 molar version.
Yeah, so then, so kind of let's take what you were saying. So let's say we have, you said 0.01 molar. And that would have to be of, right, our strong acid, HCl. So exactly, you would have a 0.01 molar concentration of H plus ions. And then we can just take negative log of 0.01. And so that gives us a pH of 2 there. So good. So that's, yeah, excellent that you're seeing that connection. And so like I said, it's not straightforward for the weak acid, right? So there's equilibrium, but we're not really going there in this class. Or I'll tell you the context if we do go there. All right, so again, putting context now to everything. So gastric juices have a pretty low pH. I think y'all probably expect that since, right, it's essential in aiding in digestion. And then perhaps you already know that, like, if you ever do throw up, right, that's why they say to rinse your mouth out and, right, make sure that you clean your teeth off so that you're not having those really acidic gastric juices on your teeth. And, well, I guess no one is bulimic anymore in the days of Ozempic, but at least back in the day, right, that was kind of a symptom of bulimia, that they're poor teeth. And I mean, now I'm going to show that I'm a little paranoid about teeth enamel, I guess. And so there's also like why dentists say like don't brush your teeth right after drinking like orange juice in the morning, so that kind of the acid weakens your enamel. And so obviously, right, you don't want to scrub it with your hard toothbrush. And then so obviously soft drinks are also acidic. Y'all probably know that. Again, some of the phosphoric acid is contributing. And then most fruit is also acidic. So plums, for example, wines are also acidic. So same sort of thing, right, with the teeth enamel issue. So apples, peaches, cherries all tend to be on the acidic end. Same with beer. I don't know if anybody brews beer in here. I was just curious because I've never been into it, but I've just like known people that are into it, and I know like the pH of the water has to be pretty specific. And um, for example, like they did a pH adjustment in Medford about a year ago. So if you were brewing or something, you would at least have to be cognizant of it and potentially pH adjust or something. And then you probably know that human blood is set at a pretty precise pH, right? So it's actually a buffer solution to keep it right in that small, tight range for obviously all those wonderful cellular activities to go on. Then egg whites are basic. Milk of magnesia is also basic, right? Sometimes used for upset stomachs. Ammonia is going to be basic, of course. And then, right, our sodium hydroxide solution. And we'll talk about how to address bases directly, but they tend to have, again, right, a super strong pH of, well, 14. And so maybe you've figured out why our typical normal pH scale is 0 to 14. So that being said, sometimes you can get like negative pHs with certain substances. Again, right, we're not going to go there in this class to the fringes of research. But typically, right, and you can kind of see where this came from our KW product constant. So that's kind of why it goes from 0 to 14 then. And so like we already mentioned, one pH unit corresponds to a factor of 10 difference in acidity. We have our pH, again, goes from 0 to 14. And then, well, let's come back to this actually, because I feel like revealing everything. And so we also have POH. And so as you might imagine, right, our POH scale is the exact opposite. So just kind of take that in for a second, and then we'll go back and look at the math. So acidic goes from 0 to 14. Now our POH scale goes from 14 if it's acidic to 0 if it's basic. So exact opposite. 7 is still neutral. Okay. And so now there's a couple of different relationships. So we could go back and just think about for a second. So to your point, what if we had, let's take our sodium hydroxide solution from last week. It was 0.01 molarity. Man, sorry, the spammers are like going after me today. So 0.01 molarity. So, okay, first step, it's a strong base. So just to reiterate, when we're doing all this, fully disassociates. So we have a 0.01 molar hydroxide concentration. And so one thing we can do, other than going back to our KW, as this problem kind of suggests. So this problem, right, wants you to approach it from here again, relating it to our KW relationship. But I'll just go ahead and say, well, we could also calculate our POH. And so in this case, okay, if we have a 0.01 molar hydroxide solution, yes, we could figure out, right, our hydronium concentration. But we could also get our POH directly. So negative log of now our hydroxide concentration. So 0.01. And so that would mean that last week's sodium hydroxide solution has a POH of 2, which means that it has a pH of 12. And we didn't have to do, so we could have done this. So now let's do 1 times 10 to the negative 14 divided by 0.01. So that gives us 1 times 10 to the negative 12. Mental math that, or I'll just plug it in real quick. Oops, sorry. I got too excited. So negative log of 1 times 10. Do the negative 12. Okay, perfect. So, right, we're back to 12. Or, why I kind of wanted to reveal everything for y'all is we can also just take it to this relationship, which is quite easy to work with now. So we have the pH plus our pOH equals 14 then. And here's a minor derivation. Like I said, we'll at least just like appreciate it. So we started with our Kw product constant, took the log of both sides, so that gave us 14. And then by definition, this is pH, this is pOH. So that's how we got here. So I'll give y'all a second to at least kind of write that down. All right, so now we're going back. And so let's see if we can calculate the pH of this solution of A and B, but kind of do it whichever way you feel, right? So we could use our Kw, we could use our pH plus pOH equals 14. So I'll give you guys a minute or two to kind of go through both of those and solve it. You said OH.
Forgot to write down pOH.
Oh, this one. So yeah, it's just a negative log of hydroxide. So I'll give y'all another minute or so. All right, so what do we get for A? And how do we get there? So this one was more straightforward. So we could probably just do pH equals negative log of hydronium. So what do we get when we plug this in? So that sounds right. So you can kind of estimate, right? -4, so I imagine it to be about there. So 3 point, you said 87? 3.7. And let's just plug it in on our calculator so everyone can see. And again, right, make sure you are plugging it in with me, just in case you, for some reason, have a calculator that defaults to like not base 10. So certain calculators do operate in different bases. So just double check that everything is working out. Great. So now how do we do B then?
Just use the log for hydroxide. Wouldn't that give us the same?
Yeah, so let's go through the steps though. So we have POH, but yeah, you're right. Like it's basically the same thing. Is negative log of hydroxide, which is like I said, why I wanted to give this to you. So you weren't doing this the roundabout way, but I mean, it doesn't matter which way you approach it. So okay, so negative log of 1.3 times 10 to the negative 2. And so then that's our POH. So 1.88. And then did you just do 14 minus this? Yeah. Anybody do this way or kind of figured this was probably easier anyways. And so we should get about 12.11 for our pH then. And then, well, we're kind of running out of time. So let's just see, right? We could have also done this. I'll just punch it in on the calculator. So we can take our kW, so 1 times 10 to the negative 14, divided by 1.2 times 10 to the negative 2, right? We could have gotten this. And so this would have been our hydronium concentration. So 7.69 times 10 to the negative 13. And then plug that in, so negative log of our answer there, and back to 12.11. So that's the kind of good thing about pH, I feel, is we can kind of check, double check yourself. You kind of go in a little circle, and so I find it rather reassuring. All right, we'll probably end here for today, so we'll finish up on Wednesday of the buffer solutions. We'll kind of look at this. This will be like the most we're doing with weak acids and bases. And then we'll look, hopefully I need to save us some time to do like a titration math. And then we'll do the demo too. So of all the, like I said, the light bulb demo. And yeah, we're barreling to the end here. So are any of you taking the final in person, the lab final? Yeah, you could also go for both. I'm just trying to like gauge, and then you're only in lecture. Okay. I'm just trying to gauge where people are. Like I said, I know internships are starting and people are starting to come and go already. So just let me know. Um, I'll be here on Wednesday, and that can also be good, like just review catch up time otherwise. All right, let's end it here. Thanks again. And yeah, I don't think anyone's on stream.